Thank you for joining me for this video. I am Mr. Ish. Today will be just a concept video, a quick video that is, and we're going to be discussing whether a function can be differentiated at a given area or a given interval. So the topic here is a function differentiable has very much to do with the whole concept of derivatives, and this is just a concept video, just an elaboration of a given concept. We're going to be discussing the whole theory behind the derivative concept. Remember, the derivative represents what will eventually be the slope of the tangent line. The slope of the tangent line represents the instantaneous rate of change. And with the development of the equation of that tangent line, we are able to model or study the behavior of that function at a given point in time. If a function is differentiable, it's very much to do with the whole concept of continuity and with the concept of an interval. Check this out. A function is differentiable. A function can have its derivative done at a given point A if you have a derivative which exists at that point A. It seems like I'm saying exactly nothing really too important, but if you can get a derivative at a given point A, then you have a function which is differentiable at that point A. If we're talking about an interval such as this, A comma B, a function is differentiable on an interval if it is able to arrive or if it is able to yield a derivative at any point on that interval. If you're looking at an interval A comma B, the interval can be split up into several parts. You can be looking at A up to infinity. You can also be looking at minus infinity up to the point of A. You can also be looking at an interval which is represented by minus infinity comma infinity. You know, like how would be the interval for a trigonometric graph such as sine. It has a domain of minus infinity to infinity. So a function is differentiable on an interval if every point on that interval you can calculate a derivative. And a function has a specific derivative at a given point A, and it is able to be differentiated if at that given point A you can actually come up with a derivative. I want to show you an example of a function where it happens to be differentiable at every point on its domain except for one point, and we will look at that. If you look over here at the function absolute value of x, you know by means of a graph it has a curve, or let's just say a graph which looks like this. Intersection at the origin 0 comma 0, then it extends up towards positive infinity and minus infinity. If you look over here and the question is, if is this function differentiable at every point on its interval, or is there a specific point on this function where it is not differentiable? Well, we want to answer that question. If you wanted to do this question over here and you have the graph over there, the process by which you want to proceed is this. If you want to look at those values for this function, absolute value of x, where x is greater than 0, then you know you have to think back to the function aspect of the rate of change, you know, the f of x plus h minus f of x divided by h, limit as h approaches 0. Remember, we looked at all of this in the rate of change videos. If you think back to that and we look at these positive values, we're looking here at the interval now from 0 comma infinity, not including 0 but from 0 all the way up to infinity. Now look over here what happens. If you're looking at the positive values and we try to find the limit of this, what will we get? We just end up plugging in the absolute value in this format. We get absolute value of x plus h minus absolute value of x divided by h, and since we're looking at positive values, everything begins to look more like this. This right here is an h minus x over h, and then limit as h approaches 0. What happens to our function? We get what? The x's will cancel out. We'll get h over h, and we'll get what? 1. Limit as h approaches 0, this function or its derivative will approach 1. Remember, the whole concept of derivatives is the instantaneous rate of change. Now we've looked at the values on the interval right here, 0 comma infinity. But what happens if you're looking at now the minus values, because you do have minus values on this. If you're looking at the same function, f of x is equal to absolute value of x, but now we're looking at the values which are x is less than 0, what actually happens? Now look, when you're looking at values less than 0, we still have to approach everything in the same manner. The absolute value of a using this scheme over here, minus the absolute value of x over h. But when we incorporate the negativity of these values, we get something which is like this, because now we're looking at the negative values. You have minus and then minus x over h. When you open all of this up, you're going to get this. You'll get minus x minus h plus x over h. Now look over here, the x's will cancel out, but you get limit as h approaches 0, you get minus h over h, and our limit becomes minus 1. Here the limit was a positive 1, here it becomes minus 1. So we're looking over here now, for this part right here, we were looking at the interval minus infinity up to 0, but not including 0, but up to 0. But look over here, the right side values from 0 up to infinity generated a limit of 1, which can be represented the derivative of 1. The left side values from minus infinity up to 0 generated a value or derivative or limit of minus 1. Now what exactly would happen right here at point 0, which is what we want to find out all along? What exactly happens here at point 0, right here, point 0? Well, now you're clearly seeing that the right side and the left side values are not the same. But let me erase over here and show you what could happen at a specific point of 0 in a very conceptual manner only. We know if you're looking at the specific point 0 from the right, we're going to look at point 0, 0, 1. And if you're looking at 0 from the left, we're going to be looking at minus point 0, 0, 1. Here we're looking at values which are x is greater than 0, and we already established the fact, and you don't even have to plug in anything over here. We've already established the fact that on the right side the limit became a positive 1. And here for values which is x is less than 0, and we know we're looking here at a minus value because it's less than 0, not up to or include, it's not including 0, but it's up to and including 0. And here we established that the limit or the derivative became minus 1. So what happens that exactly for f of x, absolute value x, what happens when x is actually equal to 0? Well, we said that it does not exist, there is no limit. So this is one of those functions which is differentiable at every point on its curve except at 0. At 0, right, there is no derivative available. So on the interval minus infinity comma infinity, this function is not differentiable on every point on this interval because it is not differentiable at the point 0. It doesn't have a derivative at that point 0. And the reason why it doesn't have a derivative over here is to do right here with the concept of the corner. You have a corner in the graph. And when you have a corner here in the graph, what you end up seeing is that the right side limit, right side and the left side limit are just not the same. Because they're not the same, you have a function which is differentiable at every point on the interval except at a specific point, and that specific point is represented by the presence of that corner. Now I want to tell you a few more items in this concept video, and then we'll just wrap it up. Now I've placed two statements here on the board which are extremely important to this whole concept, whether a function is differentiable or not. Look over here at the very first statement. If a function is differentiable at point A on that graph, then that function must be continuous at A. This right here is a true statement. It's true because I will show you graphically why that is the case very shortly. Remember, if a function is differentiable at A, then f is continuous and that function is continuous at A, which means at that point you could determine a derivative, and at that point the right side and the left side limits of that function will be the same at that point A. But look over here, the opposite of this statement is false. The opposite of this statement is false because in some instances if you reverse the statement it's true, but in many instances it is not true. What would the converse statement be? It would be that if a function is continuous at A, then it must be differentiable at A. That's not a true statement because when a function is continuous at A, there are some instances where f is not differentiable at A. Where f is not differentiable at A. And I just showed you the very first instance was the absolute value graph, because here the function was continuous all the way around. A continuous function is one which has no break in it. It could just continues from one side to the other side within its domain without a break. Look over here. It is continuous by every mean, but it's not differentiable at all points because it's differentiable at all of these minus values and all the positive values, but it didn't happen to be differentiable at point A. So the converse statement for this was actually false because if a function was continuous, it didn't necessarily have a derivative at every point on the interval because this did not have a derivative at point 0. Another example, like look over here. Look over here. This is an example of a sine curve. If it extends towards positive and minus infinity, now look at this first statement. If a function is differentiable at any point over here, then it is continuous at any point, and it's true. There's no aspect over here. So long as this function is continuous, the statement will always hold true. That so long as this function is continuous, you'll always have every point on this interval, minus infinity to infinity, where for this sine curve, you can always determine its derivative. You cannot find a situation where you cannot do that because it's a continuous function and every point on this curve is differentiable. But look over here at this type of graph. If you have a graph which looks something like this, a function which looks something like this, right over here, it's continuous from right over here, minus infinity, up to this point 0, it's continuous, and then from 0 up to infinity it's continuous. But here at the point 0 we have a discontinuity. So if a function f is differentiable at every point, then it must be continuous at those points so long as there is no discontinuity or some other type of aspect in the curve which makes your function non-differentiable. And I want to talk about 3 aspects which make your function non-differentiable. We'll look over some quick examples and that'll be the end of this video. So let's think back to what I just said in the previous part of this video. If a function was differentiable at a point A, it was definitely continuous at that point A. So remember, if you can do a derivative on a point on your curve, then at that point the function happens to be continuous. There's no break or there's no sort of formation in that curve which prevents you from doing the derivative. And then we know that the converse or the opposite of that statement is not always true, therefore that opposite statement becomes false. But there are functions that are continuous at a given point like A, but they're not differentiable. And here are three types of examples. 2 of them are continuous, 1 is discontinuous. So this statement over here applies to this over here, and it applies to this over here, this graph over here, the function. Now look over here. When you have the presence of a corner or like a kink, this statement will take effect. There will be a situation where your function is continuous because there's no break in it. It's a continuous function at point A, but you will not be able to determine the derivative at this point A because of the presence of a corner or a kink. You know, like a kink in your curve. And the reason why you won't be able to do that is because the right and the left side limits will not be the same. Therefore, you won't be able to get a derivative over there. But look over here at this function over here. This function is a continuous function. There's no break in this. There's no discontinuity in this function. And again, this statement holds true. There are functions that are continuous but not differentiable at that point A. The reason why you can't do a differentiation of this because of the presence of a vertical tangent line. Vertical tangent line. If you look from right over here to right over here, we can't have a presence of a vertical line, like a graph which would have an x equals a. And you know what we know about x equals a, they're vertical lines. If you try to convert an x equals a into a y equals mx plus b, you can't do it because the slope is undefined. Think about it, the slope over here. The slope is always undefined for vertical lines because the change in y divided by the change in x, there is no change in x. You get a situation of change in y divided by 0. Hence, you cannot do a slope of a vertical line and you'll have vertical tangent lines. And what is all this differentiation about? It's all about determining the slope and or the equation of a tangent line. If you cannot determine the slope of a tangent line because you have a vertical tangent present, because of this situation where your slope will become undefined, because vertical lines have a no change in x, you end up with a 0, then therefore by that fact you cannot determine the differentiation at this specific point A on this interval. This statement here again takes true that your function is continuous but it's not differentiable at that because of the presence of a vertical tangent line which will come into place. Remember, all vertical lines x equals a form have undefined slopes. Horizontal lines y equals b have a slope of 0 because there is no change in y but there is a change in x. That's fine. A slope of 0 is legitimate. But a slope of y over 0 is not legitimate, it's undefined. Now look over here. We have a clear presence of break here at point A, and at this break we cannot do the differentiation because we'll have right and left side limits will be different. Look, if you do the limit as these x values approach A from the left, we'll have a very different value over here. And as x values approach A from the right, as we are approaching from the right, we'll have a very different other limit. So this instance is showing you that the right side and the left side limits are not the same. Here's my left side and the right side. The right side, left side limits are not the same. Therefore, you cannot do a differentiation over here. And this type of function with a break in it at point A is not differentiable. So the 3 situations where you need to be wary of where a function is not differentiable are these. The presence of a corner or a kink in your graph. The presence on your graph where you can have a vertical tangent line, a hypothetical vertical tangent line come into play, you're not going to be able to differentiate at that point. Or on your function where you have a break. the right and the left side limits will not be the same. Even here you won't have right and left side limits. And also keep in mind, very close to this kink, you can get very close to formation of a vertical tangent line. You can also end up seeing that, especially if this corner is a very steep corner, you can towards the end or the apex of that corner or that kink, you can end up seeing vertical tangent lines. And look over here at this other situation which I'm going to show you right over here, especially as you're getting close to vertical asymptotes, what's exactly happening. If you have a function which looks like this, you have an x equals a vertical asymptote, and you have a function which comes and grazes up and extends towards positive infinity, and you have another function which is coming over here and extending towards minus infinity. Look over here, limit as x approaches a from the left, your function approaches positive infinity, and look over here, limit as x approaches a from the right, your function will start approaching minus infinity. And the reason why it's not differentiable at this point a, represented by this x equals a, because as you start getting closer to here, you'll get vertical tangent lines, and you'll see there's a discontinuity in this graph over here. You have a discontinuity, and you will see that the right and the left side limits are not the same. So you can have functions where for multiple reasons you have an area or a specific point on your total interval where at that specific point your function is not differentiable. So keep that in mind. Let's look at some quick examples and then we'll end this video. So I have laid out here just hypothetical graphs. All we have to do is looking at these graphs where we have to just make the judgment if the function, both of these functions are differentiable at all their interval points or over their entire domain, or is a function non-differentiable at specific points. And then we just have to say at those specific points where it's not differentiable, the reason why. It's easy, it's not hard at all. If you look over here, we have this x equals 0 line. We see that there's a break over here as the right side and the left side approach minus infinity. For this first function, let's call this a. It is not differentiable at points. These are the points where a, we're talking about if this is present over here. If we can do the derivative of this function at point A, it is not differentiable. Again, I'm saying it is not differentiable over here at these points. If you look over here at point A equals 0, because here you have a break over here, and you'll have the presence of a tangent line coming into place. Because as you get closer and closer to this infinity, these two lines or these two curves, as they're dipping down towards minus infinity, they'll become too extremely vertical or very close to being vertical, as you can have vertical tangent lines come into place. And not to mention we have a break over here, so it's discontinuous. At another point where it is not differentiable, this function is not differentiable right here. Look, 1, 2 at a equals 3. A equals 3. Why? Because we have here the presence of a corner and kink. So this function a is not differentiable at 0 due to a presence of discontinuity where vertical tangent lines can occur, but the right side and the left side limits will still be minus infinity. But it is not differentiable also at point 3 due to the presence of a corner or a kink. Where you'll have this corner and kink, you can have right side and left side limits not being the same. You cannot do differentiation at these 2 points. 0 and 3. Let's call this function b, and look over here. This function is not differentiable at 2 points. Look over here. If this is minus 1, this is minus 2, it is not differentiable at a is equal to minus 2. Why? Because of the presence of a corner, and at a equals 0, right here 0, where x value is 0. Why? Because of the presence of a discontinuity. Our function is discontinuous. It is not continuous over there. The left side and the right side limits are totally different. So at these 2 specific points, you won't be able to determine the derivative of this function, but at any other point, so long as they remain continuous and free of kinks and corners or vertical tangent lines, you will have a clear derivative. So the finality of our video, the concept video, ends with these 2 examples over here. We have to determine again if these functions have any points where they are not differentiable. And we'll call this function c, we'll call this function d. When we're looking at c, it is not differentiable at 2 points, and we have to give the reason why. If you look over here at this a value of a equals minus 1, a equals minus 1, it is not differentiable because we have a break. Remember, I've talked about 3 reasons. You can have a corner or a kink, you can have a discontinuity or a break in your function, or even like a jump. Sometimes they call it a jump. Or you can have a presence of a vertical tangent line. But here at a equals minus 1, we have a break, so it's not going to be differentiable. The left side and the right side limits will not be the same. And we have another value. Look over 1, 2, and 3. At value 3, we have a downward facing corner. We have a kink over here. that the graph kinks downward right here. You'll have again a situation where you cannot do a derivative at this point, but at any other point other than a equals -1 and 3, you will have a differentiable function, but at these 2 points you don't have it. But let's look over here. The not scenarios over here are this, whereas your function is not differentiable for graph D. Look over here, -1, -2. At a equals -2, it is not differentiable because again we have a break in our graph. And look over here, 1, 2, 3. A equals 3, and with this break over here we have a different right side and a different left side. This could be y1 over here, the limit as x approaches -2 from the left, it approaches y1. As x approaches -2 from the right, it approaches this value right here, which would be y2. Totally different limits, right side and left side. Anyhow, looking over at 1, 2, 3, at a equals 3, we have a presence over here of a vertical line, x equals a type of formation occurring, where we'll end up with a vertical tangent line. And you know vertical tangent lines are no-go when it comes to the differentiability of a function. So at a equals -2 we have a break, at a equals 3 we have a vertical tangent line which would take effect. Therefore at these 2 points your function is not differentiable. At any other point your function is differentiable and you will be able to determine a derivative. So pretty much that's it for this concept video. Again, remember the fact, if you can determine a derivative at point A for any function, then your function is continuous at that point, but not necessarily the reverse. If a function is continuous, it does not mean that at all those points of continuity your function is differentiable, because you can have situations where a function is continuous but you cannot determine the derivative. 2 of those examples are corners and kinks. The other one is that of a vertical tangent line, because you have a continuous function here but you can't do a derivative of a vertical aspect of a line, or x equals a, because vertical lines have no slope, they have an undefined slope. And here in corners and kinks, it's nearly impossible to determine a derivative or a slope because the right side and the left side limits will not be the same. So keep all of that in mind. Functions, if they have a clear derivative, then at that specific point they have a clear continuity, but no more than that should be stated. And you should never be looking at the reverse as being true, that just because a function is continuous, it does not necessarily mean you have clear derivatives over all the values in that domain. That's not always true. So keep all of these in mind for this concept video, and I hope you enjoyed this video. And after this video we will go into our derivative processes, and you will enjoy those even more. Thank you for watching. Have a nice day.